Okay, good evening, ladies and gentlemen. Welcome, a warm welcome to our first online meet and greet tonight with Copenhagen Atomics. It's definitely not our first meet and greet. We have meet and greets, had them rather a few times most of them in the Netherlands, Delft. This time it's the first time online, and I'm very happy to do this together with Copenhagen Atomics. So, ladies and gentlemen, let's not delay any further and have Thomas Jam Pedersen share his latest knowledge on the development of and visions on development of thorium and molten salt reactors from Denmark. Thomas, the floor is yours.
Then this should work. You should all see a thorium ball in a hand.
Yes.
If everything is correct. All right.
Yes.
So I'm sure many of you know this story already, but just in case there's just one of us who doesn't know it, I will quickly start here and say that what really brought many of our attentions was this image of a ball this size that can supply you with all the energy you need for your entire lifetime. Not just electricity, but everything for heating your home and cooking your food and all the products you need and all the transportation and your share of all the roads and houses and hospitals throughout your entire life from that little ball. And that is very amazing. And then when you get to know that it's thorium is an element in the periodic table, you get it out of the ground through mining. And we were to mine thorium on an industrial scale, you can get this ball for around $100. It seems like the question poses, why are we not using this already today? And this is where many of us started, and this is what we will talk about the next roughly 35 minutes, how Copenhagen Atomics see that this can be used and how we can create those reactors or machines that convert thorium into energy. I want to start with a quick slide about our team. This is the core team of Copenhagen Atomics. Several of us are available here today, and we will be later for the questions and answers. You will be able to pose questions for all the members. Copenhagen Atomics was founded 5 years ago, and we are still a very technical core team, and that's of course because there's been a lot of technical discussions and also development in the past year. But one of the things we want to start to do, we are currently running an investment round, and on the other side of that, we are going to enlarge the team with more business people with a business background, commercial background. I want to start the slideshow here because I think it's important that you know where we are coming from, what we see as the problem. So part of the reason for wanting to bring thorium to the table is because this pie shows you how the energy consumption in the world is today, where 80% of all the energy is coming from fossil fuels, and a little bit from nuclear, and even less from wind and solar. And of course, a lot of people, and I should say that it has been like this for more than 30 years, and it's likely to continue in this way for many years to come. And the question is, of course, what will it take to change that pie? What will it take to make nuclear, or hopefully thorium energy, 20% of this pie? And this is what we are going to talk about also. But in the previous slide, I said that is a small problem, and this is a bigger problem, namely that the growth of energy demand around the world is increasing really rapidly. And of course, so we were lucky in the OECD countries to have a lot of growth in the last almost 100 years, but now we are stagnating a little bit in the growth of energy production in the OECD countries. But at the same time, the rest of the world, and especially Asia and Africa, is growing really rapidly. And the growth now in those regions are much higher than it ever was in the OECD countries in the past. And of course, that gives a great opportunity for startup companies like ours, because this is a big market, and it's expanding. So there should be a good chance to get some market share there. And then finally, I also want to show that, so one of the drivers for this is, of course, human population growth. And when you start to look at this, you see that Asia and Africa is really going to be the majority of the people in this world. Basically, already by 2030, it's roughly 80% of global population, and from there on, it's just going to increase. So those are the primary market for new energy installations in the future, because of course these people in those regions also want to have electricity, running water, air conditioning, dishwashers, transportation, all these nice things that we have. And we should also remind ourselves that when we look at energy consumption in different countries today, a lot of the products that we consume in Europe, for example, are manufactured in Asia, and therefore the energy to manufacture those products are actually not put on our sort of energy chart. Anyways, I also just want to mention that the energy market is really big. It's a little bit over $10 billion per day. So that's a lot of money. And many people from Denmark know the wind turbine company called Vestas, and their entire life of that company, the total net income was roughly $10 billion. So that's, yeah, one day's energy consumption. If you go on the street in many developed countries and ask the general population about what they think about classical nuclear power or just nuclear power, many of them will tell you that it's dangerous or that it's very expensive. And when we build power plants, it always plagued by cost overruns and delays, and they produce a lot of waste that is difficult to handle. And those of us who work with these know that this is not the entire truth. It's definitely not as dangerous as it is perceived by the public. In a matter of fact, nuclear power is one of the safest, if not the safest, energy form if you measure it in death per megawatt hour produced. So it's not exactly super dangerous. It's rather the opposite. And also the waste is not as bad as people think it is. And that's those misunderstandings are, of course, because there's a lack of information. And I encourage you to talk to your friends and relatives and neighbors and colleagues about this, because we really need to get people to know a little bit more about radioactivity. When you listen to the media, a lot of time they just kind of assume that everything that is radioactive is dangerous, and this is not true. And I don't want to go in detail in explaining this. I'll just say that all the things in the blue box are things that you meet on a regular basis in your life. For example, eating bananas, getting dental x-rays, flying on an airplane. And of course, none of these are dangerous, but this is where you meet radioactivity in your everyday life. And the things in the green box here is also things that you might meet, like, for example, living in a concrete house for a year. And also the things in the green box, even the big part here is the maximum allowed radiation for nuclear or radiation workers in the US. So none of these things in the green box are dangerous, and they won't kill you. We can, of course, measure it, but that doesn't make it dangerous. But of course, when you get down here to the red box and the yellow box, it starts to get dangerous, and these radiation levels should only be handled by professionals, trained professionals, and there should be rules and approvals and regulations about how to handle this. But they are actually already in place. So yeah, we just need the public and the media and the politicians to realize that these up here are not dangerous. But that's a long effort. About the nuclear waste, it's a big debate what you want to call waste, but I want to highlight that if you run a classic nuclear reactor like this one on uranium, first you need to mine a lot of uranium out of the ground. Then you need to enrich that uranium. And when you enrich it, you get a lot of uranium 238 or depleted uranium as a byproduct. And some people call that waste, and Greenpeace or somebody like that will even call it dangerous waste, but it's a very natural product. It came from nature and it didn't change. It's still the exact same as when it came out of nature. So and it's not very radioactive also. Anyway, so the enriched uranium fuel, you put that into your reactor, you run it for a number of years, and then what you get out on the other side is fuel rods consisting of these different components. And there you see that most of what comes out again is again this depleted uranium, which is the same as this one, and which is exactly the same as what came out of the ground some years earlier. So again, you can debate whether this is waste, but again, by many governments and other parties, this is considered waste. And it's not from physical point of view that it's waste, it's more from a legal point of view. Anyways, it also contains these other parts, the uranium fuel, which has value and should be used in a good way. And then it contains fission products, which in the beginning, just after it's unloaded from the reactor, they are quite radioactive, much more radioactive than this depleted uranium. But of course, they have a very short half-life, so the radioactivity of the fission products decays away fairly fast. And then there's the last part, the transuranics. These are in general what makes this whole thing that people call waste a problem, because transuranics are radioactive for many years and needs to be handled safely for, say, 100,000 years. There's not a lot of it, but there are some. And this is actually what we want to use in Copenhagen Atomics. We want to use this part as a Kickstarter fuel for our Copenhagen Atomics waste burner. And by mixing thorium and transuranics, we can start the waste burner and let it run on that. And then eventually it will produce a lot of energy. And the energy will help pay for this processing of this fuel, such that we can separate out the different things. Because part of the reason in the old nuclear industry today is that it's quite expensive to do anything about this. And there's no incentive for anyone right now to actually process that. The only country that does process this is France, and from my knowledge, it's not super economic, but they still choose to do it. Anyway, so from the Copenhagen Atomics waste burner, we get, when you put 1 ton of thorium in, you also get 1 ton of thorium out. 1 ton of fission products out. And because it's in on a salt medium, you can actually do processing of this and separate things. And if you were to separate it in this way, you would get most of it, 83% is fission products that has a very short half-life. And after 10 years, they're stable, and then it's not radioactive anymore. Then there's some parts that are radioactive for a longer time, and they need to be stored safely for 300 years. We humans know how to do that. That's not a big issue. And then finally, there's a little bit of transuranics, 100 grams per ton, and that needs to go back into the waste burner. Otherwise, that would be considered waste. But if you put it back in here, then eventually, after a long period of time, it will also be split and turn into fission products. I also have this chart where I try to compare thorium molten salt reactors with classical nuclear, and this is kind of just a big highlight. So it's not exact numbers. It's kind of just the first principle. So you approximately need 100 times more mining for a typical classical nuclear reactor than you do for a thorium waste burner. And here you need enrichment, and of course enrichment can be used for also for military purposes and bombs. So there's some concern that enrichment is problematic. It also uses a lot of energy, and you need a very pure form of uranium to do this. So it takes a lot of effort to do that enrichment process. And for a thorium waste burner, you don't have that. Again, the amount of waste, the volume of the waste is much bigger here than it is for a molten salt reactor. And the waste also needs to be stored for, some people say 100,000 years, where the comparable down here is 300 years. And then the price of the building all these buildings is very different, because these molten salt reactors can be built on assembly lines. And you can do, by doing that, you can really get the price down. And if you look at the number of components that are in such a machine here, it's actually, there's less components that you find in a high-end car. And the world already produces 200 million cars a year. So we can easily produce a lot of these on an assembly line if we want to. And that is also why we say here development speed. You know, what is the maximum we could get up to if we humans really wanted to deploy these fast? And then we believe that we could potentially reach 1,000 times faster. But this is only from a physics point of view. Of course, there's also political side of this, and maybe it's problematic with this in terms of policies and politicians and approvals and all, and you know, getting the public opinion sway. And then finally, molten salt reactors run at much higher temperatures, and this means the conversion from heat to electricity can be much more efficient. And just for complete, I've also made the comparison between thorium molten salt reactors and thermal spectrum uranium molten salt reactors, because a lot of people ask about this, and I wanted to make kind of a comparison. But it depends, of course, on exactly what design you try to compare. So you should take these numbers with a little bit of a yeah, there's some uncertainty in here. But of course, if you want to run something on enriched uranium, you still need to dig a lot more uranium out of the ground. You still need to enrich it. You still get a lot more waste because it doesn't, you get a lot more transuranics when you burn it in this way. And then of course, you also have the long storage time if you're not able to separate it or do something about the transuranics. But the rest of the parameters are more or less the same. In Copenhagen Atomics, what we want to build right from the beginning when we started the company is molten salt reactors that can fit inside something that is approximately the size of a 40-foot shipping container. And it should be built on an assembly line. And we believe that we can make these with 100 megawatt thermal power. What happens when you build these on the assembly line is that you can get, of course, very good quality control and also improve the product over time. And when it's sent out from the assembly line, it's not radioactive. So you can send it on normal trucks and ships. And when it gets to the destination where it's supposed to run, it's put down into a concrete shaft underground. And then you load the thorium molten salt into it, which is not very radioactive. And then finally you load a little bit of Kickstarter fuel. And then the box, after that, the box is sealed 100% gas tight, and it's not supposed to be opened for all the many next years when it's running. Only when you have to take it back to the factory and recycle it, then it needs to be opened. I also want to give kind of a timeline of how we see the development in Copenhagen Atomics. Many of you might remember that we did a demo in Delft in 2017 with one of our first molten salt loops. And then the year after that, in 18, we had the first demos and tests of our pump. Copenhagen Atomics has spent a lot of resource to develop a unique pump, because when we looked at the results or the reports from the MSRE from the 60s, it showed that one of the components that was a problem and where there were some things they wanted to change was around the pump. They had problems because the pump was leaking gases, and they could potentially contain radioactive gases. And there was also getting grease from the bearings was getting into the interior of the pump and causing corrosion. So they said this was some of the things that needed to be changed. And of course, now we are 40, 50 years later, and Copenhagen Atomics, we looked at that and we said, we need to develop a pump that doesn't have any seals at all. And that's what we've done. And we've patented that very carefully. And that's a really unique product for molten salt reactors, because in our view, the two most critical components in a nuclear reactor is the pump and then the heat exchanger. Then in 2019, we started testing all the components that are supposed to go into our first reactor. So it's a lot of testing to make sure that the components work. And sometimes we find problems and we fix those and we run the tests again. And one of our big milestones this year in 2020 is to start our 9,000 hour test, which is basically a test where we run the components for an entire year without stopping. And once we are confident that this works well, we are going to build a non-fission prototype. This is also what we are raising money for now, to build a non-fission prototype in a 1-to-1 scale with all the components, so that we can test all the components together in one system under the right conditions, the right temperatures, the right salts, the right pressures, all that, and make sure that everything works. Once we've done that, we're going to raise additional funding and select a country where we could start our first molten salt reactor, and we believe we can do that by the year 2025. And after we've started the first molten salt reactor demo, we believe this is going to be approximately a 1 megawatt test reactor. So it's not a commercial reactor that produces electricity for the grid. It's merely a test reactor that shows that we are able to build these and run these. And then from there on, we will start to build the first commercial reactor, which is a 100 megawatt reactor. And if all goes well, we believe we could have that online by 2028. And this chart shows a little bit the expected revenue in Copenhagen Atomics. Already today, we are selling products. We are selling these molten salt test loops that I will show you a little bit later that we use for testing components, but also other teams working on molten salt use for testing components, not only in molten salt reactor market, but also in molten salt energy storage market. Is there quite an interest for these type of systems to test different components. And you can see here that we're going to grow the revenue. It's really important for Copenhagen Atomics to be a company that doesn't live from investor money only. We want to make sure that we have some revenue, and we also want to make sure that as soon as our products are ready, they get into the market and they can prove their worth and prove that they're working in a real market with real customers, because that's a much better test than if we just test all our components in our lab. And that would help make approval agents later on, really trust our products. If, for example, a pump has had 1 million hours in the field before it goes into the first commercial reactor. Here's a little bit from the budget from Copenhagen Atomics. You can actually find some of this information online, so I won't go too much into that. What we focus on in Copenhagen Atomics is, of course, building components, and the long-term goal is to build molten salt reactors on assembly lines. But on a day-to-day basis, what we're always talking about is, how can we minimize the risk for investors? And basically, that problem is the hen and the egg problem, where politicians, politicians don't really want to support this until there's enough voters who are also willing to support it. And the public is waiting for proof of concept of this technology. And the developers are waiting for money to build the demos. And investors are waiting for the risk to get to a lower point, because a lot of investors today see that the risk in this field is too high to invest a lot of money. So this is why everything is moving slowly. And of course, the majority of the risk in this field is related to lack of political decisions, both about using this energy form, but also about what are the approval requirements for these reactors. That is a bit unclear for developers. So this is what we are working on, and we saw early on that one of the ways to kind of break this evil cycle here is to invest in reducing the risk related to corrosion, high temperature pumps, heat exchangers, and also related to supply chain and the team itself. So this is what we have been working on for the last 5 years. And I also want to point out that, how people, a lot of times they ask, how expensive is it to build the first test model and basically show proof of concept. And it costs about 10 minutes of global energy supply to build, for example, a 1 megawatt demo reactor. So, I mean, that's not a lot of money in when you look at the bigger scale of things. And it should be possible for us humans to set aside this amount of money and actually build a demo and show to the public that it works. And then eventually, to build, to move on from there and build a commercial reactor, we expect to take the company, Copenhagen Atomics, public on a stock exchange and raise something in the order of 300 million euros. So that's a little bit longer term goals. This will likely be around 2025. I also want to point out how we see that Copenhagen Atomics has a little bit different development philosophy than some of the other groups that are working on molten salt reactors. Many of the other groups are following this gray line where they first seek money to build a team, and then they start building a paper design. And once they have a kind of a paper design, they seek more money to go through a pre-approval process. And then once they hopefully have a pre-approval, then they raise more money to finalize the design. And then they send it to a real approval process. And then hopefully eventually it gets approved. If there's not a number of iterations there, eventually it gets approved. And then they can raise even more money to start building a commercial reactor. And of course, there will be changes at this point after the approval. and then each one of those changes will cost $1 million or more. And that's why we have chosen to take a different approach in Copenhagen Atomics, where we wanted to start out with a small cash flow or cash burning, so that where we, build the different components and test them over and over again. Of course, we use as many components as we can off the shelf, but there is not a lot of companies that supply molten salt reactor components for a non-existing market that is already approved for nuclear. So actually many of these products is either improved versions of something that already exists, or they are redesigns of something that is not made for nuclear. So this is what Copenhagen Atomics has been doing for the last 5 years, simply iterating over the different component designs again and again, and tested very carefully. And we've spent a lot of time and money on this. Eventually we get to a point where we think, okay, these components are ready for building a non-fission prototype, then we're going to do that. And then, we also start to build a real design at that point. And once we have a non-fission prototype, then we are ready to start the real approval process with the company's approval agency. But it's much more fun for some agent that is going to approve our design, where they can actually go to a real physical model and test the different things, and they can ask us what happens if we increase the temperature or the pressure or something, and then we can actually do that, and they can be there while we do the test, and they can see the results for themselves. This is a much better approach than having to go through endless amounts of paperwork. Of course, there's also going to be some paperwork in this, but we believe in this dual approach where we also build something in the real life. Then at some point we get it approved, and we're going to build the actual 1 megawatt test reactor. And the thing to say about that is it's a lot easier to get an approval for a 1 megawatt test reactor that is going to run only for a shorter amount of time than if you wanted to get an approval for a commercial reactor that is going to run for several years. So that's why we think we can do this faster, and also because we already have the supply chain in place and everything. So this is our development philosophy, and by doing this, we also believe that we can collaborate with a lot of the national labs and universities, and maybe also some of the other startups around building components and building out this industry. Now I will show just a quick video of from our lab, and now I need to make sure that everybody actually see the video. Okay, so what we have here is this is our workhorse in the lab. It's molten salt test loop version 5, and you can see some of the older versions in the background there in our lab. And what we use this loop for is for testing components and measurement instruments and gaskets and materials. So what we have here is a tank at the bottom, a pump, and a test chamber, and we can circulate the salt around and around in there. What we looked at there was the furnace where things get up to 700 degrees hot. Now we're going to show some images of molten salt. The first one here is a nitrate salt. Nitrate salt is also the ones used for concentrated solar power plants and molten salt energy storage systems. This salt is a FLiNac salt, which is a fluoride salt, which is one we use a lot. Here you see a loop where we're pumping the salt around. Unfortunately, there's a lot of droplets at the window, so it's a little bit unclear. Here's a better view of another loop where we're pushing the salt around. In this case, it's 700 degrees hot salt, and you can see that it's glowing red hot. But when we made this video, we also turned off the light in the lab. Here is an example of a nitrate salt that we're heating up in the fume hood, and soon you're going to see a video or see how it looks when it's molten. And basically it has the same viscosity, or very close to the same viscosity as water, and it's also transparent. Of course, it has a higher density. The density of nitrate salt and FLiNac salt is approximately 2 kilos per liter, whereas when we're going to run with the salt in the molten salt reactor, that's going to be lithium fluoride, thorium fluoride salt, which has a density of 4 kilos per liter. Now we're going to show some images from our materials testing. We have a lot of these furnaces where we test either salts or components, or in this case, it's a silicon carbide pipe at 800 degrees. And we're going to do thermal stress testing of that pipe. we do a lot of different material testing, both corrosion testing, but also testing like this, if it has any problems when it's heated up and cooled down. And especially we've seen that for many components, there's problems when you have thermal cycling many times over. And then we're going to show a little bit from our assembly line production. We are co-located with a big international company called Alfa Laval here in Copenhagen. We actually located inside their inside the fence, and we have access to their production facilities. And we, for example, here we show TIG welding, and we also have access to laser welding of stainless steel. We built most of our components in stainless steel 316 because that is an excellent material for testing. Once we get to a real commercial reactor, we probably need better alloys, but for now, this is a really good material. Here you see some images from the production line of our loops inside the. This is the same workshop where Alfa Laval is also manufacturing some of their things. You saw some of those in the background there. So that concludes my video, and now I'll swap back to the slideshow. I hope it shows correctly now. I will just spend a lot of times when you hear about thorium energy maybe in the media on YouTube or something, you hear people trying to explain thorium energy in 1 minute. And of course, that's difficult. I mean, I think everybody recognizes it's difficult to explain in 1 minute. And therefore, I've decided we want to spend just a few minutes to explain how we see it, because at least that allows us to present it the way we think it should be presented. So first of all, what we're looking at here in this image is the thorium fuel cycle. And down here 9 o'clock, we get thorium into the fuel cycle. Thorium comes out of the ground, and because of the way thorium reactors are, it doesn't need to be super pure. And then once you hit that thorium with a neutron, it can absorb that neutron and turn into thorium-233, which is over here 9 o'clock. And that decays through radioactive decay down to protactinium-233, which is an isotope that is not found in nature. And that has a half-life of approximately 30 days. So eventually this will also decay down to uranium-233, which is also an isotope that is not found in nature. And this uranium-233 is a really, really unique isotope because it has some great properties. When you run your reactor in thermal spectrum, every time you fission one of these uranium isotopes, it gives off 2.3 neutrons. And this is what you need to get the process going, because you need one neutron to go down and bring the next thorium into the cycle, and you need one neutron to go through your moderator and back and split the next, or initiate the next fissioning of the next uranium atom. And I said 2.3, it's because you need a little bit of additional neutrons, because you are going to lose some neutrons in your process. But this means that thorium is the only element on the planet which can start this cycle where you can have something where you have basically a positive breeder cycle in thorium spectrum. You cannot do that with uranium or any of the other fuels. So this is what makes thorium really unique. And this is why we like thorium. And also there's also other reasons, but this is the main reason. So if we compare that to how uranium works in the uranium fuel cycle works in classical nuclear reactors, basically you have to enrich the uranium in the fuel rods. And then once you've done that, you can start the reactor. And then after 1 year, you have burned some of your fuel, and that turns into fission products. But in that process, you also convert some of the uranium-238 through a uranium fuel cycle to plutonium, different versions of plutonium. And then as you burn the fuel over several years, you get more and more of the fission products, but you also get a little bit more plutonium, and you burn away your uranium-235. Eventually, when you get to this point, the process cannot run anymore, and you have to stop your reactor. But you still have 94% of the uranium left in your fuel rods. So this process is not able to burn all the fuel, and it's also not able to create a breeder reactor. And it's this part down here, the worst part of what is left over. This is what we want to use as Kickstarter fuel in our waste burners. And this is why it works so well, because we want to work down here in this, what is called thermal spectrum, down where there's kind of slow neutrons. And you can see here that plutonium-239 is really, really good in this region. In some cases, it's 50 times better than uranium-235. That means that the likelihood that an atom will fission when you hit it by a neutron is 50 times higher. And of course, here in the thermal region, it's much better than out in the fast region, where you really need a lot of neutrons to make it fission. And that translates to either you need a lot of neutrons or you need a lot more fissile fuel if you work out in this region. We are not super big fans of fast reactors because in the world of nuclear reactors, we have built many hundred thermal reactors, and almost all of them have worked. And we've built, the world have built approximately 20 different fast reactors, and almost none of them have worked successfully. Some of them never got up to full power. A few of them got up to full power, but have not really become a commercial success yet. So this tells us that it's just from a technical point of view, it's a lot easier to make thermal reactors from our point of view. But of course, we hope that in the future, we will be able to make fast reactors as well, but also make fusion reactors. Yeah, it's not that we are totally against it. It's just that we prefer to invest our efforts over here. And I will also just point out that in this thermal region with this neutrons, uranium-233, it's much better than any of the other fuels in this region. It's where you get on average 2.3 neutrons out of the process. And this means that you get a really good neutron economy, which you can use for either creating breeder reactors or creating reactors that are waste burners or produce very little waste. Okay, so that was the quick introduction to how molten salt reactors work, and especially thorium molten salt reactors. Of course, that could be a whole 10 hours discussion if you wanted to, but I have to limit myself here. So now I want to talk a little bit about the history behind Copenhagen Atomics. We were founded at the Technical University of Denmark back in 2014. Before that, we'd had a lot of meetings in bars and cafes where we discussed the subject for a number of years. And then in 2015, we did our first public talk about molten salt reactors and what we wanted to do with Copenhagen Atomics. And in 2016, we were actually part of a European application called Mimosa with some of the partners from the Netherlands and other European countries to raise money for doing research. And we were really happy that we were part of that, and we got to learn to know many of the people working with molten salt reactors around Europe. So that was great, even though the Mimosa project was not funded. That was still a positive experience. Then in 2017, we had the first loop demos, as I mentioned before. In 2018, we sold our first products, and we also had the first versions of the pump up and running in a stable manner. And in 2019 was a big year for Copenhagen Atomics. This is where we made a collaboration agreement with with Alfa Laval. Alfa Laval is a big company in the world that produces a lot of different products, and all of them in stainless steel. And one of the things they are known for is they are world leading in heat exchangers, and they also already make heat exchangers for other molten salt applications. And we want to help Alfa Laval prepare and make heat exchangers for molten salt reactors as well. And also in 2019, we were granted 2 research grants from the Danish government to do research on the pump and on purifying salts. So we got more than €1 million in research grants last year. And those research projects are going to run for the next 3 years. And some of the partners is the Technical University of Denmark. It's another pump company. I say another one because Alfa Laval actually also has a pump company. I will get back to that soon. This is a quick image from the production facilities where we get our components manufactured. And the important thing about this is a really high quality production facility. Most of what they produce in here are things for food processing, very pure food processing, and sometimes even processing of things in the medical industry. And they have some really good skilled workers for welding and milling and so on. Copenhagen Atomics today is located in this building. We have the entire ground floor here. This is where we have many of our labs, and we have a workshop there as well, offices and so on. And I hope some of you, if some of you become investors in Copenhagen Atomics, we want to invite you to come and visit us and see our lab. So I hope some of you can get a chance to do that someday. I just want to briefly mention some of the products from Alfa Laval, because it's actually a really good match with Copenhagen Atomics and molten salt reactors. These heat exchangers here in the middle are called plate heat exchangers, and the special thing about these are that they are stainless steel brazed plate heat exchangers. Alfa Laval has some patents on that, and they're the only company in the world that can make these type of heat exchangers that can work at very high temperatures. They would work well for molten salt reactors. You can see a cross section of it here, but Alfa Laval also manufactures a long range of other heat exchangers, which you can see here. This particular one on the lower left-hand side is a printed circuit heat exchanger. And I mentioned briefly also that Alfa Laval is also manufacturing stainless steel pumps for the food industry. They are one of the leading manufacturers of pumps for high purity food products. And they make many other products like valves, and this is a decanter. It's a machine for separating fluids, so you can separate fluids of different density. And then I just briefly want to mention that Copenhagen Atomics is now running a funding round on a web platform called Thunderbeam. Thunderbeam is a platform that allows regular people to invest in startup companies, especially startup companies, before they go on a regular stock exchange. And we are one of the companies featured there right now, and we have an open investment round. You can go online and find out a lot more about it. There's already 140 people who have invested in Copenhagen Atomics through that platform. So that concludes my presentation, and now I look forward to some questions and a debate about molten salt reactors and thorium and the things we work on in Copenhagen Atomics. And I think now Aslak and Peter will join in for maybe some of the questions.